Today we're talking about derivatives and graphs. You can actually look at the graph of a function and say things about the derivative. You know, last time we did a bunch of finding derivative by doing a bunch of simplifying of things with the limit. That's pretty taxing. You can look on the graph though and sort of eyeball what the derivative is. Let's take a look. How about this function? All right, how about this function here? Now, I'm not giving you an equation for the function. Just by looking at the graph, though, we can say what certain values of the derivative are. Remember, the derivative of this function represents the slope on the slope of the tangent line on the graph. So, for example, can we say, so this is a picture of f of x. Can we say how about f of minus 4? Well, that just means what's the y value when x equal minus 4? It's over here. This is minus 4. The y value is 0. So this is 0. All right. What about f prime of minus 4? That little prime makes a big difference. This is something completely different from f of minus 4. F prime of minus 4 is the derivative, the instantaneous rate of change. It is the slope of the tangent line, according to the graph here. What you want to look at is the tangent line to this graph. What is its slope? Well, and specifically at this point right here. So what you should do is you can think in your mind or draw on your graph. Try to draw in the tangent line. Remember, the tangent line is the straight line which touches the curve only at this point. Just barely, meets up at that point, and that's all. So here, I would say the tangent line looks something like this. Now, if you're drawing this on your own paper, it might look slightly different, depending on precisely how you drew your picture. And now that line, anyway, what is the slope of this line? The slope, remember, is the rise over the run. Now, if this were on like graph paper, you would be able to say pretty specifically what the slope was. Here, I'm just asking you to kind of guess, eyeball this. What do you think? If you go over 1, how high up does it go? It looks to me like if you go over 1, you go up 1. Like this, to me, looks like a 45-degree angle line. So I'm going to say the slope of that is 1. That's because this looks like a 45-degree angle line going up, and such a line has slope 1. I hope you're familiar with slopes from high school or whatever. All right, so this is what I meant by you can actually look at the graph and kind of try to eyeball what the derivative is. How about, let's look at f of 2. F of 2 and f prime of 2, all right? Remember, these two things are completely different. There's really very little relationship between these, like as numbers. You should not expect them to be related at all. F of 2 means what is the y value. F prime of 2 means what is the slope of the tangent line. Very different. What is f of 2? The y value here is 0. This one also is 0 for its y value. But f prime of 2 is the slope of the tangent line at this point. So I'm going to try and draw the tangent line as best I can. This is all just estimates, really. You are just trying to eyeball the slope of this now. What's the slope? If I go over 1, how high up does it go? Maybe 3. So to me, it looks like this, the rise over run will be 3 over 1. So this one, I'm going to say 3. Again, if you drew this picture on your own paper, the slope here is probably slightly different on yours than it is on mine. And this is just a guess. This 3 you can't say very specifically, but certainly you can tell the difference between 3 and 0. How about 0? Are there any points on here where f prime equals 0? I think there are. That would mean the tangent line has slope 0. I hope you remember. Slope 0 means like the rise over run actually is 0. That is, the rise is 0. Slope 0 means that the line goes just flat horizontally. So can you see any points on this graph where the tangent line is just this flat horizontal line? Actually, I see 2 such points. It would be here and here, right? These points, so here the tangent line looks like that, and here the tangent line also looks like that. These are flat horizontal tangent lines. That indicates that the derivative is 0. So you would write that by saying f prime of, in this case, the x value is 1. So f prime of 1 is 0. And also this other one is x equal minus 2. So also f prime of minus 2 equals 0. Okay. One more question about this guy. For which x values is f prime of x positive, and for which x values is it negative? Let me get rid of these guys here. All right, look at the x values. For which x values is the derivative positive? That means the slope of the tangent line is positive. If you recall, slopes being positive means they go up and to the right. Slopes being negative means they go down and to the right. So on this picture here, let's talk about where is the slope negative, first of all, just because it's a little easier to say the answer in this case. F prime of x is less than 0 for x. Such a situation or such a question, I usually want you to give me your answer in terms of intervals. So for x in the interval, do you see any values where the tangent line slope is negative? That means it's going down as you go to the right. Actually, I do see some values. There's many points, like for instance right here, the tangent line is going down as it goes to the right. Where are such points? Can you say like where they all are? They actually make an interval. How about you ready for some movie magic? The points where the tangent line is less than 0 would be right here. That's where the derivative is negative. Where is, so as an interval, this range here, if you write that as an interval, it would be from x value -2 up to x value +1. So as an interval, it's like that, -2 to 1. I write this as an open interval. This means all the x's that are between -2 and 1, not including those two endpoints. It's not including the endpoints because at the endpoints, the derivative actually equals 0. And I'm saying here it is less than but not equal to 0. So really, it should be an open interval. What about the positives? F prime of x is positive on the interval. This time there's actually two separate intervals where it's positive. There's this range here and then also this range over here. Both of those places, the tangent lines are going up as they go to the right. So I'm going to say this is the interval from 1 up, everything greater than 1 as an interval. That's written 1 to infinity. And also this one over here, everything less than -2, that would be written as the interval -infinity to -2. All right, that's how we do that. All right, here's the original function, f of x, and your job is to draw a graph of the derivative. If you're going to do this, it will work best if you draw it just directly underneath. Draw the graph of the derivative. So this second picture is going to be a picture of f prime of x. Now, and you want to sort of line up these two pictures vertically. It will help you to represent important features on the original graph need to be represented on your graph of the derivative. This is all going to be slightly informal just because it involves looking at the slopes and sort of estimating what you think the slopes are at various points. Now, the first thing that you should do in such a case is to find the places where the slope is 0, because that doesn't really involve estimation. You can see very clearly where the slope is 0. It would be here and also here, right? These are places where the tangent line is horizontal. And there's actually, I tried to at least to make it so that there's a point here where the tangent goes straight horizontal. All right, so these are 3 places where the derivative equals 0. I'm going to say this is the important sort of first step. Find where f prime equals 0. These are horizontal slope points on the original graph. All right, and since down here I'm drawing f prime, that means what I'm drawing down here, it must be 0 at those 3 points. So whatever I draw down here, it should be 0 right here. By it should be 0, I mean like the y value should be 0 down here, because in this graph the y values represent the slopes. All right, this one should be 0. Also this one should be 0. Okay, so your job really is to sort of draw in some curves that connect up these 3 points. This is a way to give you something to get started with. All right, how do we connect the dots when I draw the curve in between? Well, you got to ask yourself, for example, between these 2 points, you kind of have 2 choices. Either it should go, because it's not going to be 0 in between, because you don't see anywhere else. Either it's going to connect the dots like that, or like that, right? This is probably, it's going to be one of those 2 things. how do you tell which of those two things are? It has to do with looking at the slopes here and deciding for yourselves, are the slopes positive or negative? Remember, positive means going up as you go to the right. Negative means going down. And you can see pretty easily on this graph whether they are positive or negative. In fact, it might be helpful to say whether they're like really positive or just a little bit positive. Really positive would mean very steep slopes. A little bit positive would be going up but not very steep. And similarly with the negative. Going down but not very steep would be only a little bit negative. It would be more negative if it was steeper. Check it out. I'm going to try and indicate that by drawing little P's and N's. P for positive, N for negative. So along this stretch here, it will be positive this whole time, right? Because the graph is going up and to the right. I would say it's very positive down here. So I'll write like a big P, fairly steep, whereas up to, nearby here, it's quite a bit less steep. So I'll write like a little p. Can you tell the difference between my big P and my little p? So it's very positive, and then it goes down to being less so positive, and then right there it's 0, right? We already said that's what was special about these 3 points. The derivatives are 0. And then in between here, it's going to be negative because it's going down and to the right. I would say it's a little bit negative at first, then becoming more so negative, that's a big N, and then again becoming just a little bit negative as it approaches that point. All right, and then in here I'm going to do a similar thing. It's a little bit positive here. It becomes more positive, all right, with a bigger P. And then it becomes, again, just a little bit positive. I know it's hard to tell between the little p and the big P. I'm trying. I'm just a simple man here, drawing on a piece of glass in my basement. And then from the 0, I'm going to the right. It begins off being a little bit positive and then quite a bit more positive as we move off to the right. Okay, can we indicate that in terms of curves down here? Actually, I was asking before about these two. Which one is it? Is it this one which goes up here or this one? Well, what I'm going to draw down here has to be negative, meaning the y values have to be negative, a little bit negative, and then more negative, and then a little bit negative again. Actually, that's this one. These ones have positive y values, so it should be the one that goes down there. And this shape of it actually obeys what I said it should. It should be a little bit negative, and then more negative, and then just a little bit negative again. The y values here are a little bit negative, and then they become more negative, and then they're just a little bit negative. All right, how would I draw between these 2 points? It should be, the y values that I draw down here should be a little bit positive, then more positive, and then a little bit positive again. That should look like that, all right? And then the y values, as I continue to the right, they should be a little bit positive and becoming more and more positive. So they go up, and then they continue to go up, right? A little bit positive, followed by more and more positive. And then I'm almost done here. I got to draw something over here. What I see here is very positive, and then a little bit positive. So I want to start actually up here, very much positive, and then becoming a little bit positive until you get to this point. All right, that's the answer here. Now, if you sort of step back and look at this, you may be tempted. I'm going to tell you about a temptation you may feel in your heart. I'm here to tell you, don't go there. But you may be tempted to say, well, oh, this thing is like a lump going up. And down, and the answer, it looks like a lump going down. That's true, but you should regard this as more or less a coincidence. When you're doing a problem like this, there really is no kind of shortcut. Oh, I can just look at this curve here goes up and then down and then up again, and so it goes down and then up, and then you might feel like you can convince yourself that there is some kind of simple catchphrase which will allow you to do these without thinking about it. I think there isn't. If you really think you've figured out some sort of mystery of the universe, let me know, and I will be happy to discuss it. I have nothing against simple catchphrases which let you do the thing in an easy way. I'm into that, but for this kind of problem, there isn't such a thing. You've got to actually break it down and think about the various chunks of the curve. All right, I want to talk about 2 more kinds of things that you might see on the curve which make this a little bit more complicated. All right, here's another example. What's different about this is it has an asymptote. I want to talk about how do you handle asymptotes in an example like this. Well, notice that as the graph approaches this asymptote, this graph has to go down like infinitely far down before it hits this line. What that means is the slope as it goes down here will have to get infinitely steep as it approaches this line. That means when you're drawing the graph here, the slope will also approach an asymptote in the same spot. So when I draw my answer down here, I'm going to begin by putting an asymptote in the same place. All right. So how do you handle asymptotes? I'll write the slogan over here. So this is for handling a vertical asymptote, a vertical tote in f of x. This is the original function, and what I'm drawing down here is the derivative. A vertical tote in f of x makes a vertical tote in f prime of x at the same place. Right? The asymptote here causes an asymptote in the derivative at the same x value. Okay, otherwise I'm just going to do the same stuff. Begin by identifying where the slopes are 0. I see a point here where the slope is 0. Elsewhere, I don't see anywhere else where the slope is 0. I'm looking for horizontal tangent line. Okay, now I'm going to try and indicate where the slopes are positive or negative with my p's and n's. Here the slope is very positive. Here it is less so, only a little bit positive. Here it is a little bit negative. Here it is very negative, becoming like infinitely negative, super duper negative over here, right? What about here? This slope here is also super duper negative, right? Because it's going down and very steep. So here, very negative, less so negative down here, but again becoming more negative over there. Okay, let's see if we can draw it. First, mark off the 0 points. There's only one here, and that will be at a 0 down here. This is like the previous example. And then I'm going to try and draw a line which obeys these p's and n's. It should be very positive, then only a little bit positive before it hits that. That means it looks like that. Very positive, and then only a little bit positive. And then it should be a little bit negative, more negative, super duper ultra negative. That means it should do something like this, right? A little bit negative, more negative, and then eventually super negative. Okay? Great. That's the picture on the left side of the asymptote. What about over here? Now, actually over here, I don't have anything to get me started in terms of like a 0 value to stick there. All I see here is negatives. It should be super negative, then a little bit negative, and then super negative again. You just have to draw that. Something you want your y values to start out being ultra negative. That is, they have to approach the asymptote anyway. So it has to be like that, right? And then less so negative for a bit, and then more negative again. So something like that, right? Super negative, less so negative for a little bit, and then more negative again. Okay. Jumps and points and segments is what I want to talk about here. This is what I mean by a jump in the graph. This is what I mean by a point. That is, the graph for some reason makes us like a sharp point like that. And then segments, I mean line segments. Part of this graph actually just looks like a straight line, and you'll see that will have a certain kind of appearance in the derivative. Again, your job is to draw the graph of the derivative, and you should line them up. Everything is easier if you line these up. Now, again, I'll write over here what each feature makes happen here. Okay, so jumps and points, they look very different on the graph, but actually you handle them in exactly the same way when you're drawing the derivative. Jumps and points in the original function f make jumps in the derivative. And I said in parentheses, always empty circles. I'll tell you what I mean by that in a moment. And straight line segments make straight horizontal segments in f prime. These are the rules. I'll explain what I mean by those in a moment. We're going to begin, as usual, by identifying points where the derivative is 0. That gives you a place to get started, at least. I see one such point right here. So when I draw the derivative down here, eventually I'm going to make it go through 0 right there. Elsewhere, I don't see any such points. All right, we can still make this happen, though. Let's try to identify where this is positive and negative. So right here, it's very negative, going down steeply, becoming less so negative here. Although the slope, it remains negative all the way up to this point, right? And then after this point, it suddenly becomes positive and stays positive throughout this whole straight line segment here. And then at this point, it suddenly becomes negative. It's actually quite negative here, less so negative there, 0 right there, and then a little bit positive and more positive. Okay, so these are sort of the positives and negatives that we're going to have to indicate down here. What I said is jumps and points in f make jumps in f prime. You can see because the derivative here is very negative, becoming less so negative, it is going to go something like that. Very negative, becoming less so negative. But then, at this point, suddenly the derivative becomes positive. It never was 0, but the derivative goes just from being negative to being positive. And so that means there's going to be a jump up to positive here, right? This is why I said always empty circles. This is what I was talking about. When you draw the jump in the derivative, it should have empty circles on both points. That's because if you filled in one of them, it would mean like the derivative actually is here and not here. But here, there is no derivative at this point. Because of the break in the function, the derivative is always undefined at such a point in the function. So we get a jump in the derivative, and it jumps from being negative to positive because here you can see it was negative and then it's positive afterwards. Okay, how about what happens throughout this straight line segment? The interesting thing about a straight line segment is all of these points have the same slope because it's a straight line. And in fact, in this particular example, along this straight line segment, can I just say here, the slope is 1, right? I tried to draw this so that it looks like a 45-degree angle going up. And so when I draw the derivative, its values should be 1 always throughout this little range here. So until this point, the value I'm drawing here is always y equals 1, which causes it to look like a constant function throughout that range, a straight horizontal line. That's what I meant. Straight line segments in f make straight horizontal segments in f prime. That's why I drew this. Straight horizontal. That's because the slope all the way throughout this range is always equal to 1. All right, now I see this point that causes another jump. We jump down to become very negative and then slightly less negative until we're 0. So it should jump down to here and then go up to there. And then I want to see slightly positive becoming more positive. Something like that. All right. That's that. These are a little tricky. Got to practice that.